Boker Tov. Good morning, Tel Aviv. My name's Gabe. As Azure said, I am the lead program manager for the Azure Container Compute team. So I'm responsible for many of the different services in Azure, both product strategy for those services. My counterpart actually on the Azure team is a guy by the name of Brendan Burns. Anyone know who Brendan is? Anyone ever heard of Brendan? Brendan is the co-creator of Kubernetes. So it's basically myself, Brendan, working on containers, Kubernetes, cloud native strategy, and products inside of Microsoft. So very lucky to be here. Very excited to share with you some of, sort of what I've learned doing this work in this space for many years. Also share a little bit about some news that we've announced recently at KubeCon in Barcelona and elsewhere. So let's go ahead and jump right in. My whole career has really been about empowering developers. I started off on the operations side, helping design and scale large systems for many different software companies, doing lots of different kinds of consulting. But always in mind for me was, how do I take a team of software developers and make them more productive? I've been doing this for at least 15 years, probably 20 years. I can see the gray hair here. I've been doing this for a little while. So I have developed a big passion for how we can make developers more productive. Now, one of the most interesting things about my job today is that I actually sit on the board of the Cloud Native Computing Foundation, where I represent Microsoft. Anyone here familiar with the CNCF? Show of hands. Okay, the CNCF is very interesting because this is an open source foundation that houses intellectual property for some of the most important technology, open source technology on the planet. This is where all of the intellectual property, trademarks, domains, everything like this is stored for the Kubernetes project. And what's fascinating about the CNCF is that it's the only organization where you have Microsoft, Amazon, Google, IBM, Oracle, Alibaba, basically the entire industry has all joined this foundation to promote the advancement of open source technologies like Kubernetes. It's really the only place where we can all get in a room together and talk about how we can advance the industry, provide portability to our customers. So inside of this room, where I represent Microsoft, I learn a lot about what it takes to be a good open source citizen, how important it is for us to not just take from the open source community, but also to give back, sometimes with technology, but also other times just by doing what we like to call chop wood, carry water. Now that means, for example, right now the Kubernetes 1.15 release is being in the process of being cut. Microsoft engineers are some of the people that are actually driving the Kubernetes 1.15 release. This is part of what we mean by chop wood, carry water. It's important for us to give back. And my job and my role in the CNCF helps make that more apparent. Now, inside of the CNCF, we all like to think of ourselves as creating building blocks. Building blocks, cloud native building blocks that all snap together neatly and allow enterprises and startups and folks who are building innovative technology to do so with open portable blocks that all snap together nice and clean. This is what we aspire to. I think unfortunately, the reality is that from the perspective of a developer, it looks a little bit more like this, right? Lots and lots of pieces, Legos all over the floor, you step on them, ow, that hurts, right? This is what it feels like today to work in the land of cloud native. And it's unfortunate because I think there's a lot more that we could do to make these pieces interoperate together better. But today this is still a confusing time. So I always like to think in these situations about prior art and what we could learn about things that have been done in the past. Because in these technology cycles, we tend to keep repeating things over and over, the same thing. And when I think about prior art, I often think about some of the PaaS platforms like Cloud Foundry or Heroku. And I think about the developer experiences that were enabled by these platforms and how exciting and fun development was. Anyone here ever use one of those PaaS platforms like a Heroku or Cloud Foundry? Anyone? No? A few of you? It was a joyous experience, and it still is for some. The problem, though, with these platforms was that they were ultimately a black box abstraction. And what I mean by this is that if you were operating inside the bounds of what the PaaS was designed to do, in most cases a 12-factor app, life was good. Things would work well, you'd be happy. But the truth is, most modern applications can't live inside of that constrained environment. And what happens is when that abstraction fails you, when you need to break out of those chains, you have to fall all the way down to virtual machines, typically. And that fall from a PaaS system down to virtual machines tends to be very painful. And so, this is something that I had learned, and this is actually why we started building PaaS systems at Deis, the company that I founded, that Microsoft acquired about 2 years ago. Now, at Deis, what we decided was that it was important for us to build platform as a service to empower developers on top of a foundation like Kubernetes that provided a container orchestration layer. And it was important that that layer be something that the developers could go directly to in the event that the 12-factor PaaS abstraction failed them. And so this actually turned out to be a very good approach. At one point, we had the PaaS system working on top of Docker Swarm, on top of Mesos, on top of Kubernetes. And as a result, myself and the entire team at Deis had a ton of experience operating Mesos and Docker Swarm and Kubernetes at very large scale, working with companies like OpenAI, for example, on their very large Kubernetes clusters. Now, it turned out this was a very good model. But as we were in the process of building and working with customers on this PaaS, what we started to realize that the market was really shifting radically towards Kubernetes. It was this technology that was just taking off like wildfire. And so we learned a lot about what it takes to operate Kubernetes at scale. We have upgraded and managed and maintained some of the largest Kubernetes clusters on the planet at this time. It was about 3 years ago, let's say. Lots that we learned here. But probably the biggest thing that I learned was when you roll Kubernetes into an environment, it's less about the technology choices, and it's more about what Kubernetes and Cloud Native does to the operating model inside of your company. Now, I like to think of this as what I call the Cloud Native operational model. At the bottom of the stack, you have infrastructure operations. This is where you deal with raw compute network storage. And if you're unlucky enough to not be able to work in cloud, sometimes you have to actually physically rack the servers and wire up the networking and all this. Today, most people get to use IaaS from a cloud provider. They don't have to worry about that. But there's still a role, a function, an operations job around managing IaaS. Now, on top of that compute network storage, there is now a new job role, operations role that's being developed. We call it the platform operations team. And when I go around the globe meeting with lots of different customers, I meet these platform teams. You know it's a platform team that you're talking to when it's clear that their job is to take all this cloud infrastructure and turn it into a platform for developers to build upon. And in fact, if you're working with Kubernetes, very oftentimes the team that becomes proficient in Kubernetes will take on this job, whether intentionally or not, of turning all of this infrastructure into something resembling a PaaS. Now, the most important part of this to me, and the part that people tend to miss a lot, is that at the top of this sits an application operations function. This is where developers actually have to take on some level of operational burden for how their application is going to run in production. How is that application going to be monitored? How are you going to alert on it? How are you going to deal with canary deployments? How are you going to deal with the different types of issues that can happen at the app level, which are separate from at the platform level, where there's a whole different set of failure modes and concerns that typically a platform team will take on. Now, if there's one thing I've learned, it's that companies that succeed with Kubernetes and Cloud Native understand this model. They adapt their organization to deal with this model. And the ones that fail, largely it's because they do not. They view the adaptation of containers in Kubernetes as purely a technical problem. They don't think at all about how the operations function inside their organization might need to adapt or change. So I definitely recommend you take a look at this. And in fact, what I hear most commonly is that most people doing containers in Kubernetes are already deriving some form of this model. I think probably the best way to sum this up is you need to work towards a you build it, you run it model. This is how we deliver services inside of Azure at scale. AKS, Azure Container Instances, managed OpenShift services. Everything that we do, the development teams that are building these services are also in charge of operating and running these services, carrying pagers, right? This is the future of software. Now, I want to talk about some specific lessons that I've learned around different areas, and I want to start off with version control because I think it's a very critical topic. Who here is familiar with the term GitOps? All right, well, GitOps is the idea that your operational functions will be all living inside of Git-based version control. This is a very popular pattern. This is something I definitely recommend. And I actually think the most important part of GitOps is not that you can recover your environment from checking out a branch, although that is important. I do think the most important part is that every time you make a change to your infrastructure, whether at the platform level or at the application level, you can use a pull request and a discussion on the pull request to get buy-in from everyone in your organization. The collaboration around GitOps is the most important part. Then, of course, when you merge and the code pushes out and your pipeline pushes your changes out to production, that's also quite a nice benefit. But it's the collaboration features that are critical to this. Now, there's two patterns that I've noticed for how this gets rolled out in the wild. One is an operation-centric repository. This is where all of the manifests, all of that describe the application deployments will live inside of one or a few repositories that are managed by a central IT function, an operations function. Now, this works okay. This works okay in environments where the developers don't typically have access to production systems. But it's not the only way to work, right? This works in centrally controlled environments. But in some environments, for example, in Azure, we have application-centric repositories where the source code that is being deployed and managed out to production actually has the Kubernetes manifest, the Helm charts, things like this, located in that same repository. And that means every time the code is changed, you can also put in a change to the manifests, and you can have a seamless deployment out to production at the application level. Now, I want to be clear, there is not a right or a wrong, right? Operation-centric repository, application-centric, this is just a mapping of how your organization is laid out. Do you have a very strong, controlled central IT function? If so, then maybe the ops repository is right for you. Do you want to empower your dev teams to sort of take the pager and run their applications all the way out to production? If so, check out the application-centric repository. I also want to talk a bit about scaffolding. Scaffolding is the idea of how do you lay down information into your repository so that your developers can get productive with containers and with Kubernetes. There's a few things that I've learned. One is that it's very important to have some tooling that can provide detection heuristics. In other words, how do you look at a source repository and determine what the right Docker file is for that repository, what the right Kubernetes manifest or Helm charts are for that repository? Now, you could ask your developers to write these things themselves, and often this is what we do. But if we're going to reach more and more developers over time, we can't force them all to learn Docker and Kubernetes. We're going to have to figure out how to provide tooling that's going to provide a happy path that gets them up and running quickly. This is what detection heuristics can provide. Now, ultimately, what will happen is those heuristics can provide something like a default file system layout, where there is a, for this Python application, here's the Docker file in the repo. It understands how to read the package, requirements.txt in the repo. It understands the manifests that are required for the Kubernetes services and deployments that are going to be co-located with that application. And all the developer has to do is fork and clone the repository, insert code here, and to set up their pipeline and deploy code out all the way to production. This is going to be critical if we're going to actually get more and more developers onboarded onto this cloud-native technology. Now, of course, the trick with this is that the minute, as a platform team, the minute you do this and the minute you have a developer fork and clone a canonical repository, you now have lost a little bit of control over what's in that. So if you want to make a change to the Kubernetes manifests, you now have a delta that you have to worry about tracking over time. This is challenging. There aren't very good tools and very good solutions to this. I can tell you that Brendan and myself at Microsoft are working on ways to improve this. We can't share anything just yet, but we do have some improvements in the pipe. All will be open source, of course. Now, I also want to talk about the development process. One of the things that I learned at Microsoft when I first joined, we have this division inside of Microsoft called Developer Division. This is the group that builds IDEs, like Visual Studio Code. Anyone here using Visual Studio Code? Okay, lots and lots of hands going up. I also use Visual Studio Code. I think it's the best IDE on the planet. I think it's the best IDE for Go development. It's extremely popular everywhere I go. And so the folks that are building those IDEs and debuggers and runtimes, they taught me these terms called inner loop and outer loop, and I want to explain what they mean because I think it's very important. The first is this term outer loop. Now, outer loop refers to when you are working with source control, after you make a change and you merge that change into a mainline branch, you will kick off typically a CI process, a process that will build source, test artifacts, maybe even deploy artifacts out to production. Outer loop is a largely solved problem in the Kubernetes space. You know, whether you're using Jenkins or Azure DevOps or Circle CI or CodeFresh, there's lots and lots of different tools out there that can provide solutions for outer loop. Well-solved territory. Now, what's more interesting to me was when I learned that there was another term that they used called the inner loop. The inner loop is the period of time where a developer has not yet ready to commit their code, but they're still typing on the laptop, right? They're still trying to figure out what it is they want to commit. They're not ready to make any merged changes. How do you actually do inner loop development on distributed systems that are as complicated as Kubernetes, with dozens and dozens of microservices, who knows how many different backing stores, lots of different production data inside of those services? This is a hard problem. And I actually think the hardest part of this problem is actually doing the testing in the inner loop. Because, like I said, it's hard to replicate the array of backing services with any level of fidelity. You know, the idea that you're going to be able to replicate this on your laptop, replicate production on your laptop. I'm sorry, but most of the people that are doing real microservices, and I don't mean, you know, 2 websites, I mean real microservices, you know, 20 services all calling each other, 50 services with a 10 service call graph, right? If you're getting into real microservices, how you test during the inner loop becomes a very, very difficult challenge. And so what I've learned is that there's a very simple approach I like to promote for this. The first is you want to unit test your code locally, right? Unit testing is a very good idea. Do it. But unit tests typically run in memory on your laptop, and they have to complete quickly. What unit tests cannot do is they can't test the aggregate of your system. And when you try and make unit tests, you know, you can experiment with mocks, you can experiment with things like this, but it becomes very challenging. So instead, the best thing to do is to integration test your code remotely. And what I mean by that is spin up environments in Kubernetes namespaces, drop versions of your application into Kubernetes where they can interact with some of the live production services or services in your staging environment. This is how you're going to get confidence that the changes you're rolling out to your distributed system are going to be safe, that they're not going to break things. It's very important and something that we've built a lot of tooling. So anyone here familiar with a product called Azure Dev Spaces? Anyone here familiar with a product called Draft from some of my open source teams? These are both tools. Draft is an open source tool. Dev Spaces is sort of an Azure product that is built off of an open source tool. And both of these tools provide solutions for how you can do integration testing remotely in a clustered environment. I recommend checking it out if you haven't already. I want to talk about CI quickly. Now, I think it's important that as an industry, everyone starts to put their CI configuration in the source control repository with their code. Too many people I've seen will set up a large Jenkins build farm or Azure DevOps or something, and they won't actually put the config for CI in the repo. They'll put it in the config of the tool. And what ends up happening is the minute that server goes down or the config gets wiped, you lose everything. And really what you want is you want the config in the repo so that the next time you have to recreate your environment after a disaster or to stand up a new version of your environment, you just add repo, add repo, add repo, add repo. There we go. So I do think it's very important that CI config lands in repositories. I also think it's important that mentally, as you approach CI, you think about how you can focus your CI system on artifacts. I remember when I was building CI systems back in New York City in 2005, 2006, at the time, CI was all about artifacts. It was about building artifacts, testing artifacts, publishing artifacts to a central store. Deployment was never part of the deal with CI. But then somewhere along the line, someone decided, wait a minute, if I actually just put a deployment at the end of this pipeline, it's going to make my green build a green deployment. Isn't that convenient? I have a nice UI for deployments. And yes, it is convenient, and yes, it does make sense, but it's also not the intended purpose of CI. So I actually think it's very important as an industry that we think about how you decouple continuous integration from continuous delivery. They're different processes. In fact, it's very hard for us as an industry to create reproducible software that can be packaged and delivered to software consumers if we don't figure out how to publish software in a third-party location and then have people pull that software down to consume it. This is an art that I feel like has been lost over the last few years, in part because software as a service companies are so used to pushing, creating software and pushing it straight out to production that we've lost a little bit of the art of the artifact. We'll also talk about continuous deployment. I view my job at Azure as trying to make it safe to deploy software, safer to deploy software, specifically out to production. There's lots of techniques that we can use, and there's a couple I want to share with you. The first is around smoke testing. Smoke testing is very important. I think at every stage in deployment of complex distributed systems, it's important to have some level of smoke test. Now, what do I mean by smoke test? I mean, before you run a piece of software or you advance a deployment or any change to a system, you want to run a component and blow some smoke at it and see how things work out, right? In fact, things like Kubernetes health checks inside of deployments are a level of smoke test. But there's more. When we were building the day as PaaS, which was a very complicated set of many different microservices, we had many levels of testing. We had unit testing, we had functional testing, we had integration testing, we had E2E testing, 4 different levels of testing. And some of that included some level of blowing smoke. And the amount of times we would catch bugs and problems during a smoke test and thereby save us pain in production was large. So make sure you're trying to test at every phase, including last mile deployments into production. The next is feature flags. Anyone here using feature flags to roll out software today? If you're not, you should experiment. There are lots of cool software like Launch Darkly, for example, offers a great SaaS solution for this. Feature flags allow you to decouple the delivery of software changes from the runtime application of those changes. This is, in fact, how we deliver most software in Azure today. We're able to roll out changes in software and then gate those behind feature flags that we can turn on at runtime. So for example, I can say in our Dubai data center, I just rolled out new code, but I want to turn it on in that Dubai data center only, and I want to turn it on for 5% of my traffic. And then I can look at my monitoring and telemetry, and I can figure out whether or not that change looks good. And if so, I can start a progressive rollout of that over time. But this only works if you're putting feature flags into your code. This is a very good practice and something I recommend you take a look at. It's important for modern distributed systems. And I also want to talk about canary deployments. Anyone familiar with the term canary deployment? Yes? Anyone know where it comes from? Mining, yes. Canary deployments refer to, in mining, there is a risk of bad gases being released in a mine that can actually kill you, carbon monoxide being a good example. And so what they would do is they would bring canaries down into the mine in a little cage, and if the canary dropped dead, it meant that there's bad gas in there and you need to run out. Right? And so now we talk about canary deployments as a way of, seeing if there's bad gas in your deployment, right? So, so this is a very important, and actually I think one of the keys to this is making sure that we can automate canary deployments. I'm going to show you a little bit about that, how I see that playing out in a minute. The key to automating canary deployments is observability in your monitoring infrastructure. So I want to talk a bit about how we do this. The first is I think it's very important that we as an industry provide instrumentation on deployments and health of systems like this for free. We cannot ask every developer to instrument all of their code automatically. It's not going to scale. It's not going to work. So what do we need to get for free? Well, for one, we need request throughput. We need to know how many requests, especially successful requests, are making it through a given service. We also need request latency. What is the P99 latency, the P95 latency, the P50 latency, the different percentiles? How fast is the response time to these systems? It's very important to understand if your latency is changing dramatically from one version to the next. That's one reason why you might need to fail back and roll back a canary deployment, for example. The next is error rate, and this is the most important one. Ideally, the error rate for any of your service is 0. And if the error rate is greater than 0, you know that you have a bad deployment and you need to roll that back automatically. We call these the golden metrics. The golden metrics are important because you can collect them generically, right? You can collect throughput, you can collect latency, you can collect error rate, and it doesn't matter what type of system it is. As long as it's HTTP-based, gRPC-based, you can actually collect these metrics generically. And we start to see this happening in the industry now, and I'll show you a bit about what I mean by that. I like this quote. This comes from a guy on my team named Jason Hansen, worked with me at Deis, now working with me at Microsoft. Modern applications are sufficiently complicated that they need to be flown by the instruments. I want you to think about that. Today, modern aviation, if you go get on an airplane, they can press a button and the airplane can taxi all the way down the runway, take off, land, without any intervention from the pilot, right? We need to get our applications to the same place. And in order to do that, we need to really level up our game. So I really want to do something great. I want to figure out how we can actually make this work in a generic way. So I'd like to show you something. I'm actually going to cut to a keynote that I just delivered about 2 weeks ago in Barcelona at KubeCon and share something about service mesh technology, which I think is an important advancement in the field. So if you're not familiar with service mesh, the story starts here. Smart endpoints, dumb pipes. This is how we've been building network systems for the last 25 years. The idea is that logic for your endpoints, things like compression, identity, encryption, they live inside of the endpoint. They don't live inside of the pipe. The pipe's job is just to forward packets, right? This is how the internet's worked. So you could say it's worked out pretty well, right? The problem, though, is that now we have an explosion of endpoints with the advancement of Kubernetes, container technology. How do we manage things like routing, telemetry, and policy when you have so many different endpoints? Well, you make your pipe smarter. And so what service mesh technology does is it takes things like routing, telemetry, and policy, it adds them onto the pipe, adds them onto the network as a separate control surface. So you can start to control these things on the network itself rather than having to coordinate changes in logic across all your different applications. This is a critical advancement. Now, the challenge, of course, is we have all this cool technology being developed. Istio from Google and IBM, extremely cool, lots of features. Console from HashiCorp, really great at providing solutions for VM to container connectivity and working better in more heterogeneous environments. Linkerd, anyone here familiar with Linkerd? It's a great user experience, lightweight, it's got a super cool Rust data plane, very beloved for sort of its user experience. The problem today is that when you integrate with one of these service mesh technologies, you integrate directly with those APIs. This means that you get locked in. You can't actually change between the different mesh technologies. Well, that's about to change. So in partnership with everyone on this board here, at KubeCon we announced something called SMI, stands for Service Mesh Interface. This is a standard set of portable APIs that allow you to use service mesh technology across many, many different providers, something we're very excited to showcase here. So just to hone in on the problem, if you're building applications or tooling or you're part of the vendor ecosystem, today integrating with this technology is kind of a mess. You have to perform N different integrations across N different service meshes. Now, if what you need from a service mesh can be handled by the SMI APIs, which we've now put out in open source, you can actually change this into one integration where SMI can provide an abstraction layer for things like routing and telemetry and policy. And that is radically going to radically simplify sort of the adoption of service mesh technology. You get a standard interface, and it's extensible such that as new technology gets agreed upon by the industry, we can roll that into SMI so more folks can benefit from it. Now, I want to be clear that if this sounds like not a new idea, that's because it's not. This is not a new concept. Anyone here familiar with ingress in Kubernetes? The ingress resources, yes, okay. So in Kubernetes, if you want to do north-south load balancing, you want to define different routes for HTTP traffic, you write an ingress resource, and then there is a controller that will implement, it will read those APIs, and it will manifest your intent on whatever system. And you have Nginx, Traffic, HA Proxy, Contour, Glue. There's lots of different solutions out there for ingress. And I want to point out, people are writing ingress resources. And say what you will about the API and whether it needs to be evolved or not, but they're not writing resources directly to any of those implementations. That's not what we do in Cloud Native. We don't write to direct implementations. We write to APIs and interfaces. So this is sort of what we're doing with SMI. So I'd like to show you some examples. So first I want to show you traffic split. So this is a demo of Flagger from the folks at Weaveworks doing an automated canary deployment. Up there you can see the traffic split resource where we're basically configuring the weight between our canary and our primary. And over time, what we're going to do is the Flagger tool is actually going to advance the canary weight. You can see it going up from 85 to 20. And what the SMI API is going to do, that SMI API is actually going to reconfigure the Istio traffic split behind the scenes. And what you'll see here is you'll see us progressively rolling out this canary, doing the type of automated canary deployment that I was just referring to a few minutes ago. All of this powered through a set of portable APIs with SMI. You can see here we're almost done advancing the canary. And in fact, Flagger from Weaveworks has already been updated in master to use the SMI APIs where available. So this code is actually real. This demo you can run yourself if you like. You can see the promotion is now completed. Now the next thing I want to show you is traffic metrics. This example happens to use Linkerd, but it could use any other implementation. So here you see the Linkerd console. And we have a number of services that are getting active traffic to them. And I want to show you what it looks like to collect metrics using SMI in a generic way. So the way that we built this, and this is actually built by the folks at Linkerd, is we have an aggregated API server that runs for the SMI metric spec. And that metrics is pumping out about 5 different metrics. So if you fetch those metrics, what you're going to see is there's a Kubernetes resource called Traffic Metrics now that is going to give you in real time P90, response latency, success count, failure count, all in Kubernetes resources. Now this can be used by tooling like KubeCost, which is a tool that will analyze the cost over 1,000 different requests. And so here you're seeing that it's using the SMI metrics interface to actually pull out what is my system costing me, right? How much does each request cost in Kubernetes? KubeCost, already been updated to use SMI. Now the last one I want to show you is something called traffic policy. This is using console on the back end, but again, it could be using anything. Now, here what we're going to do is configure MTLS, mutual TLS, to secure connectivity between different endpoints inside of my network. So we'll start this by starting this dashboard app is trying to talk to a counting service. And you can see it's actually failing. The service is not reachable. So the first thing we're going to do is run the SMI controller. And this is going to build an adapter that's going to configure console based on the SMI APIs. We then create this traffic target and TCP route service that says from this source to this destination, using these service accounts in Kubernetes, I want to configure an encrypted TLS tunnel between those services, and I want to apply policies such that those services can talk to each other. Now, after we apply that in Kubernetes, it gets applied as an intention in console, and you can see the service opens up automatically. The intention in console is configured, and we now have a secure tunnel between services. The inverse is also true. We can go in, we can pull down this service, and the traffic policy will get deleted. The SMI API, or the SMI controller will notice that deletion, pull the intention out of console, and the TLS tunnel goes away. We can no longer talk to the services. So that's SMI examples. And as you can see, we're using one set of APIs to programmatically control Istio, console, and Linkerd. Now, why do we think this is important? Well, I think it's really critical that we make it easy for folks to get started with service mesh technology. I think this is a very important innovation, but I think it's too hard. I think there's too many people out there who are looking at this, looking at technologies like Istio and going, this is too much. This is too much for me. I'm going to wait for this to settle out. I think we need to make it easier for folks. The other thing is, I think simpler is better. I think that most customers that I talk to actually only need a subset of what is in most service mesh technology today. I think things like traffic splitting, things like policy, things like pulling metrics between services, those are the important bits. And that's what we've tried to focus on with SMI. And I also think it's ecosystem friendly. Everyone benefits from the open source ecosystem being able to create new innovations and advance technology at their own speed. And by providing an interface layer here through the SMI surface, we're able to allow folks like Linkerd and HashiCorp to provide innovations in this space that benefit everyone. And we at Microsoft believe it's critical that we create space for the open source ecosystem to build new technology like this. So to wrap up, where do we go from here, right? There's lots happening in this space. Well, philosophically, there's a couple things I believe really strongly. The first is we really need to accept that there's going to be complexity in the stack. There is a lot of moving parts in distributed systems. What we're building today, AKS, fastest growing service in the history of Azure, literally the history of Azure. It is complicated, right? There's no way around it. So you have to accept that service mesh, Kubernetes, containers, all this stuff is going to be hard. But at the same time, we have to demand simplicity for end users. It's not good enough for us to tell everyone that in order to use this cloud native technology, you have to go to school to learn Docker and Kubernetes and service mesh and all this other stuff. We need to figure out how to tool this, how to build happy paths for people, how to create example repos that people can fork and clone and get the job done of just writing code and getting code straight to cloud. That's a big focus for us at Microsoft. Why? Well, we have a stated mission at Microsoft to empower every person on the planet to do more. That's what Satya believes. That's what I believe. I know that's what Brendan believes. We all believe this in our heart of hearts. And it's important to realize that there's about to be millions of developers that are going to walk up to this set of technology over the next few years. It depends on how you count, but could be anywhere from 10 million developers, 20 million, 50 million possibly. If we don't figure out how to make this technology easier for them, we're going to be missing out on all of the innovation and ideas that the generation coming behind us is going to be able to provide. So let's empower them. Let's figure out how to make this stuff simpler. Let's figure out how to make this technology more accessible. Things like Kubernetes, things like SMI are part of our solution for how we're going to do this, but it's only the beginning here. So that's it. Thank you, everyone. Hope you have a great show.